Again, a very warm welcome. Thank you again for joining us, for our webinar titled Automatic Model Documentation with H2O. My name is Saurabh Kumar, and I'm on the marketing team here at H2O.ai. I'd love to start off by introducing our speaker for the day. We have with us Nikhil Shekhar. Nikhil is a machine learning engineer at H2O.ai. He's currently working on our flagship product, Driverless AI, which is an automatic machine learning platform. He graduated from the University of Buffalo, majoring in artificial intelligence, and is interested in developing scalable machine learning algorithms. Before I hand it over to him, I'd like to go over the following housekeeping items. Please feel free to send us your questions throughout the session via the questions tab. We will be very happy to answer them towards the end of the session. This presentation is being recorded. A copy of the recording and a slide deck will be available shortly after the presentation is over. Without further delay, I'd now like to hand it over to Nikhil.
Thanks, Saurabh. Good morning, everyone. So I'll start with presenting my screen. Just give me a second. Can you guys see my screen now?
Yes, Nikhil.
Yeah. Okay. Cool. So we'll be going over the AutoDoc, which is a new product from H2O. So this basically is for documenting the models which you develop, including the model pipeline, feature engineering, etc. So we'll go into the details of what kind of models are supported in the AutoDoc and how the idea of AutoDoc came into picture, etc. over the course of the next 1 hour or so. Let's begin. So whenever there is a regulatory body, so there is a need to document the models that you develop, and there are multiple different challenges which people or an organization on a whole face, especially the data scientist. So a few challenges are, like, it's tedious to document each and every details of the model, like the parameters, etc., and all the hyperparameters in a format which is acceptable by the regulatory bodies. So it's tedious for data scientists. It's usually time consuming, and it needs a lot of iteration of the reviews between multiple different folks who are in charge of like building the model. Then somebody inside the organization who would be reviewing the model, and then finally you submit it to the regulatory bodies before you can use the model in production. So it's really time consuming. And then if there are multiple different teams within an organization, they might have their own template and ways of documenting the model. So the documents which get created at the end within these sub teams might be inconsistent, and then there might not be an organization level consistency in the document which is submitted by the same organization to the regulatory bodies. And also if there are multiple different organizations and the regulatory bodies which reviews the documents, they have to review different kinds of documentation which has been provided by the organizations. And since there is no template usually, no standard template, is the documentation process kind of becomes incomplete. There might be some missing parameters, or what feature engineering happened, or maybe if at the end you have a stag model, the details in the document is available only for like a couple of models and not for all the models, etc. So there are many cases the document which gets submitted or gets created for the model is incomplete, and since it's a manual process, human beings are expected to make some errors. So there might be issues with the documentation, and then it goes to the previous point that it would need several iteration of reviews for the document to be complete, so that there are no errors. And then coming into 2020 or maybe beginning 2019, there have been regulatory bodies set up in the US and APAC, a few countries in APAC and EMEA, wherein there is a compliance requirement for the companies, especially in the banking sector and the healthcare sector, wherein they have to submit the documented version of the model which they want to use for a particular use case in production, which affects the users or the consumers. For instance, the credit score, right? So it affects the end user because he might be given a loan or denied a loan. So in such cases, there are compliance authorities which are set up in various parts of the world, and then the companies who who run these use cases, like scoring the credit history of a particular customer, they need to adhere to the compliance to these authorities, and for this they need to submit the document which details the hyperparameters, the model, the features, etc., which is being used. So these are the few challenges which companies have started, which companies are facing. And since there are regulatory compliance beginning 2019 or so, so this has become a major point where all the companies are trying to focus on, because all of them need their models to be well documented, and then it needs to be like tick marked by the regulatory authorities. So these are the few challenges which companies are facing in documenting the models which they build. So there are also challenges like a company which has been using, for instance, a model for the last 10 years. So there are challenges or that they need to go back and document those models, also going ahead and submit the documentation of the same to the compliance authorities if they want to continue using the model, or they will have to deprecate it. So these are the few use cases or why AutoDoc is very important in the current world. Then this is an overview of what the H2O AutoDoc does. So when you build a model, it automatically generates the Word document which you can edit, and it has the details of algos, the techniques, or the feature engineering that happened during the modeling phase. And since it's a Word document, you can go ahead and edit it after it generates the documentation in a particular format and it can be customized to your needs. So, and then it saves a lot of time for the data scientist, because 95% of the document would be built in the format in which you want, and if you want to add a few other features, you can go ahead and add it. But the format in which which the AutoDoc gives you the final document is the one uh, which can be directly submitted to most of the regulatory bodies across US, EMEA, and parts of APAC, like say Singapore, etc. And then if it's an internal document, wherein you want to document a model for your internal use, so you can also edit it and customize it based on your business needs. And it's very simple to use, as in you will see in the next few slides how can you generate an AutoDoc for the model which you have already built. You just need to add a couple of lines of code to it, and then you get a full-fledged documented model for it. Going to the next slide. Give me a second. Okay, yeah. So the concept of AutoDoc came from our product called Driverless AI, which is an enterprise product. So it came from because many of our customers needed it, needed the pipeline to be well documented, and then we went ahead and extended it to support H2O open source models, the scikit-learn model, and the idea is to support a lot of other packages in the AutoDoc going ahead. So currently it supports these three libraries. It supports the driverless AI modeling, the H2O 3 open source, and the scikit-learn. So first, let's uh, go through how you can document the model which you are generating in H2O3 and create a document out of it. So these are the algorithms which are supported inside of H2O, for which you can create AutoDoc out of the box. So it's an XGBoost, now which everyone is pretty familiar with. So inside H2O3, we have a variant of XGBoost which can run in parallel, and then the gradient boosting machine which is internal to H2O3, and so you can generate AutoDoc for this. Then all the GLM flavors which are available in H2O3 package can also be the AutoDoc can be created for them as well, and the deep learning model or the library which is or the APIs which are there in H2O3 can also be documented using the AutoDoc. And then you can create documentation even for the distributed random forest and the stacked ensembles. So when you have an ensemble of models, the document which you get will have the details of each and every model which is there in the ensemble. So that's pretty useful, as in you don't have to go ahead and pick the parameters or the metrics, etc., of each and every model uh, of which are a part of stack ensemble. So if you have an ensemble which is like, for instance, a 20 plus models, you'll have to do the documentation for each and every model manually if you don't use the AutoDoc. But here AutoDoc will do it out of the box. It will capture all the details of all the models which are there in the ensemble. So it's pretty useful. And so the AutoDoc package is integrated into the H2O Steam, which is again an enterprise product, and it also comes as a Python package. So as in you can just do an install of the package in your Python environment, and you can start using it. There is no external dependency. As in you don't need H2O Steam as a necessity for using AutoDoc. You can just use it out of the box just by installing the Python package which is available. So if you go to the docs there, you'll find all the details of how to use AutoDoc, etc. It's just a link wherein we have all the documentation there, and with the subsequent further releases, the same documentation will be updated as and when we support uh, other models and new packages, etc. So this is a snapshot of how the AutoDoc for an H2O3 model would look like. So if you look here, it says in the middle. So it shows what all sections are there in the document. So it says that it's an H2O3 experiment, and then the first subsection is where you get the experiment overview, as in what was the data set that was used, how many columns were there, and some summary statistics on each and every column, and then you get the data overview. Then the validation strategy that was used during the modeling phase, so it documents that, whether it was a cross validation technique which you use, or it was an out of full sample that you are using, or you provided in a different test set altogether, etc. And then it gives you a feature importance of the final model. If you look at the right bottom, right, so it gives you a feature importance of which is a Shapley plot, and it gives you a scaled native importance as well as the relative Shapley importance. So these things are pretty handy, and all the regulatory bodies would want these. They actually not want. They need these to be documented when the document is being prepared. So all of this you get out of the box, and then the next subsection is the final model. So in the final model, it will document the parameter details. There's some metrics for instance, if you have use AUC as your scorer, then it will give you the AUC and a few other metrics values for the particular model. And then what were the alternative models which were built, you get some details of that, and as well as you get a PDB plot. So if you look at the top left, it gives you it shows the partial dependency plot, how it looks like. So it gives you a PDP and as well as an out of range PDP. And the top right has the prediction stats of for each and every quantile in your training data set, and then on the left bottom you have the actual versus predicted graph. So all these graphs you'll see in the AutoDoc, along with a lot of text which would be there to document multiple different things. So I'll move to the next slide. We'll have some text there. Okay, so this shows how you generate an AutoDoc. For instance, if you're using the first example is for scikit. For instance, if you want to generate an AutoDoc for a scikit model, you just install the AutoDoc package and then you import it. And then you just need to add in a line there wherein you just say render AutoDoc H2O config the best model, and you need to provide in the training data set the features and the label, and then you get the entire documentation which we went through. You get the entire documentation created for the particular scikit model. Similarly, for the AutoDoc for H2O3, you need to provide the H2O context, then the config and the best model, and then you'll get the model documented. So you get the AutoDoc by the name AutoDoc underscore H2O3.docx. So it's that simple to create a documentation for the model which you have already built. So you don't need to do anything now much except for adding a few lines of code. So you do your modeling, you do your EDA, then you do your feature engineering, and then you do your modeling. And at the end, you just add these 4-5 lines of code, and then you get the entire document generated for it. Moving to the next. So H2O, we have a product or enterprise team which is used mainly to start H2O3 clusters. So the ML, if any of our customers are using H2O Steam, they can also use the AutoDoc because it is well integrated into it. And then Steam exposes a service to generate model report for open source H2O3 model. And this model, the same service using driverless AI to generate the auto documentation. So the idea of AutoDoc, as I was saying, came from driverless AI, and then we extended it to support H2O3 models and now scikit-learn models, and going ahead we'll be supporting a lot of other models. So if you look at the screenshot on the bottom left, you see it shows you what all the AutoDoc will have. The pictures are not very clear. We'll go through them in the next few slides, but it has a lot of content, and it has a textual data. It has some graphs, and it has some tables as and when whatever is needed for well documenting the model well. So now we move on to the scikit-learn example. So in scikit-learn, so this is the first third-party model which the AutoDoc is supporting. So it's for now it supports only supervised learning models. The scikit-learn linear model which AutoDoc supports currently is a logistic regression, and then the ensemble methods like random forest classifiers, gradient boosted classifier, and the gradient boosted regressor. So we support these 4 models right now, but we'll have support for a plethora of other models going ahead. And in addition to scikit-learn, we plan to support other models or other packages as well. So if you look at the AutoDoc example for scikit-learn, so here if you look at the middle image, it says the subsections are more or less the same. There might be a few additions or a few that are missing based on what the particular library provides information about. So whatever the library can provide, we document all of it. So this scikit-learn experiment has the experiment overview, data overview, feature importance, final model, alternative models, and the partial dependency plots. So in one of the subsections, you'll have a confusion matrix if it's a classification model, and then if it's So if it's not a classification model, and it's a regression problem, then you won't see a confusion matrix. Instead, you'll see the various RMSE or the other scores which you, for the particular model. And in the middle, you see the shift detection. So if there is a shift in the data between the training and the test, then you should see the shift detection chart as well. If there is no shift detection, it will just be skipped in the documentation. But if you want to specifically have the shift detection to be there, irrespective of whether there's a shift or not, you can specify that using the configs. And then again, we have the partial dependency plot, the response rate, and the AUC on the left side. So this is for a classification problem, but the graphs would look different for a regression problem. You won't see the AUC curve, you won't see the confusion matrix, but you would still see the partial dependency plot, shift detection if there is a shift in the training and test data, and the response rate. So the AutoDoc would figure out based on the model that you built what all to show, and you can also configure what all needs to be part of the final model. We'll come to the configuration part during the latter half of the presentation. So next we'll go through a couple of examples of how the AutoDoc looks for driverless AI models. So this is where everything began. And so this is an enterprise product. So many of our customers came back to us, and they wanted their models to be well documented so that they can use it for internal use as well as to submit it to regulatory bodies. So we built AutoDoc and integrated it into driverless AI. So inside driverless AI, the algorithms which are supported by AutoDoc are XGBoost, LightGBM, TensorFlow, and so on. So basically, whatever libraries we support in driverless AI, all of them are well documented, and AutoDoc captures the details of all of them. So for now, we have listed like XGBoost, LightGBM, and TensorFlow, but that's not an exhaustive list. So if inside of driverless AI we add in new algorithms and they start getting shipped out with driverless AI, so AutoDoc would be able to capture the details of those models as well. So additional features are like this AutoDoc is included in driverless AI. It has the explainability, like it has some charts or a lot of techniques which we use inside of driverless AI to explain the model in our MLI module. So all of that is also well documented in the AutoDoc which you get for driverless AI. And also there you can customize the report, as in you can specify what to have in the document at the end of it, or what not to have. If you want some additional features to be added, those can also be added. We'll go through each of them one by one. So once the experiment, if you guys have used driverless AI in some capacity, then you would know that once an experiment completes or once your modeling completes, this is the screen which you get, the screenshot that you see on the screen. And then there's an option to which says build auto report. So if you click on it, it will build auto report. You can also configure driverless AI to build auto report automatically for each and every experiment. So once you have the AutoDoc, this is how it looks like. So this has a few more subsections. So it says like, okay, this AutoDoc was built by the driverless AI experiment, and then it gives you the name of the experiment, and then it says experiment overview, data overview. So these two are the same which we saw for the H2O 3 open source and the scikit-learn models. And then the methodology, it's something which was not there for H2O 3 and scikit-learn, because in driverless AI, once you feed in the data for a supervised learning problem, we do a lot of feature engineering. We create new features, then we do the modeling on top of those features, create multiple different models, and then finalize on what model should be part of the final pipeline. So the feature engineering details would be captured, like a high level of the entire pipeline would be captured in the methodology subsection here. and then whether the data sampling was used or not during the entire experiment, which comprises of the feature engineering plus the modeling phase. If there was any sampling done, uh, the details of those would be there in that subsection. And then what was the validation strategy that was used. So the validation strategy subsection remains the same across scikit-learn, H2O 3, and driverless AI. And in model tuning, for instance, if you're not using an auto ML from H2O 3, then you won't have a model tuning subsection for H2O 3. And in scikit-learn, if you're by default, the model tuning subsection will be skipped because scikit-learn just creates a model and it doesn't really fine tunes the hyperparameters by itself. And then driverless AI has another section called feature evaluation, wherein it captures the details of how many features were tried, what were the features which were selected to be used in the final model, etc. We'll go through most of these in the next few slides as well. And then the feature transformation which were used, whether we did a one-hot encoding or we did a cross-validated uh, mm, weight of evidence or something like that. So what were the feature transformations which were applied to each and every column or the input features which will be a part of the final pipeline model. So all those details would be in the subsection feature transformation. Then you'll have details of the final model, alternative models which were tried but were not a part of the final pipeline. And then what was if there is any deployment which you did from the driverless AI screen. So those details would also be there, whether a mojo was created which is a Java artifact, or whether you deployed it on AWS or using a one-click which feature which comes packaged with driverless AI. So all those details would be there, and then the partial dependency plot which remains consistent across H2O 3, scikit, and driverless AI. Let's go through some of the details of each of these subsections in the next few slides. So okay, so this is how the final screen looks like, and the one that we highlighted in the previous section is the middle yellow piece, like the second column, if you might say. So this experiment, the name was Airbnb. It has the training data set is called train. The target column was price. So and then there was a test data set which was provided to it, and then it created tons of features, and then it shows the variable importance in the middle, right? So these were the features which were created from the original features which were inputted into it. Like if you look at the first one here, it says 35 underscore CVTE. So then it gives you the column names, right? So it's 35 cross-validated target encoding on the columns which is specified next to it. So if you look, so it's if you see it there, right? So the name of the feature gets truncated, but when the same variable importance, when you say it in AutoDoc, it will have the full feature name, and then it's much easier to read. Otherwise, in this case, you'll just have to click on it or hover over it to see the entire name, the feature name. So in the middle section, the last section is where you click and then you get the auto report for this particular experiment. So that's what it shows here. And also you get the AutoDoc in the if you click on the download experiment summary, even that, so that gives you a zip file, and one of the files inside it is the AutoDoc. And so that's another way in which you can download AutoDoc. So now we'll go through a sample AutoDoc which gets created for driverless AI, and the various sections which we have been discussing till now. So the first subsection is an experiment overview. So it gives you an idea of, like, it says driverless AI built a stack and sample model of 2 light GVM models to predict positive review. Yeah, and then there were 4 original features which were there in the data set, and this is a classification problem, and that it took 23 minutes and 54 seconds to finish. And then in the final model, it's using none of the original features, but it's using 22 engineered features, and the experiment tried a total of 2000 plus features. So from the 4 original columns, or the features which were given to driverless AI, it tried, or it built 2000 plus features, and in the final pipeline it selected 22 features. So that gives you a high level overview of the experiment which you ran. And then the next subsection is the performance, wherein it says then what was the internal validation score. So it says 0.946 for AUC, and since this experiment did not have a test data set that was provided, so the AUC for that on the test data set is not available. And the next section, it says about the accuracy, time, and interpretability. So what was the value of these 3 knobs that were selected? If I may go back, so if you see here 6, 4, and 6, so this is what we're talking about right now. What was the accuracy, time, and knob setting value? So for this particular experiment, it was 7, 3, and 7. And then it says what kind of machine was the driverless AI running on. It says it was running on Linux and in a Docker environment, and it gives you some system details, as in like the system memory and the number of CPUs and the number of GPUs that was attached to the system, and the version of driverless AI. So this seems to be a pretty old version of driverless AI, yeah, but the version is 152. Next, in the data overview, you get some summary stats for each and every column that was there in the original input data set. So the left side, if you look, the name, so name of the columns was ID, score, etc., etc., and then it gives you the type of the data, whether it's int, string, categorical, etc., and then summary stats, min, median, max, standard deviation, unique, and frequency of mode, etc. And then you have one Boolean column, which is positive review, and it gives you the summary stats for that. And then comes a categorical column. And the next subsection talks about whether there was shift detection or not. It will tell you driverless AI can how driverless AI performs shift detection, and if there is any, it will show you the graph for the same, which would look something like this. So for this, it says significant difference detected between training and test distribution for the column H. So it's dropping this feature. So if there's a shift detection in the columns, then it will show you the shift detection graph, otherwise not. And then comes the methodology. So this is specific to driverless AI. You will not see this for scikit-learn models and H2O-3 models. So it says first step is to ingest the data, and when it ingested data, it detected the column types. Then we did some feature processing, turned raw features into numeric, and then in model tuning and feature tuning, it says they found the optimal parameters for XGBoost and light GBM models by training models with different parameters. So all this section, for instance here it says XGBoost and for light GBM the parameters were fine-tuned, but if your model uses only TensorFlow, it would say the fine-tuning happened for only the TensorFlow model. So all this text is generated on the fly for the particular model which you're trying to document. And it's not like a preset text. It's dynamic, and it captures the feature for the model which you generated, and which you're trying to document using AutoDoc. And then it says the best parameter for are those that generate the greatest AUC. So basically, we are trying to optimize AUC for this particular experiment. And the next bullet point says there were 241 trained and scored to evaluate features and model parameters. So there were 241 models which were trained and scored to evaluate which features should be a part of the final pipeline, as well as the final model which was created. And then the details of the feature evolution, as we went through in the experiment summary, 2096 features were used for over 41 iteration, and then 720 trained and scored to further evaluate engineered features. So 720 models were trained for during the feature evaluation phase is what it's trying to say. And then the final model was a stack ensemble of two light GPM models, and it did not have an XGBoost model or a TensorFlow model or some linear model. So this is the final model for this particular experiment. And then the scoring scoring pipeline, it says the Python scoring pipeline was created. Mojo scoring, which is a Java artifact, was not created for this particular experiment, and it gives you the name of the Python scoring pipeline, which is H2O underscore experiment underscore the name of the experiment, then the scoring pipeline and scorer.zip. So you can download the scoring pipeline from the UI and use it for either real-time scoring or for batch scoring. And then it says it gives you the time that was that driver, let's say, I took for each of these to do. Like for the data preparation, it took 12.86 seconds, and then for the model and feature tuning, it took 280 seconds, and 241 models were built during feature evaluation. It took 1021 seconds, and 720 models were built. So the feature evaluation is usually the step where travel essay takes the most amount of time. That's where it tries to do feature engineering and tries to figure out which are the best features. So that's a uh, pretty core feature of driverless AI, which takes time because there's a lot of models which get built there. For instance, in this example, if you see, there were 722 models built during the feature evaluation phase. So it's obvious that it would take the longest amount of time. And then the final pipeline, to create the final pipeline, it took 96 seconds. And there were 6 models which were built. So this is the validation strategy which was used for this uh, particular experiment. So there was a 5-fold cross validation which was used because the training data set was not provided, and then it create from the training, no, sorry, because the test data set was not provided. So from the training data set, it created 5 folds, and then and then each of in the subsequent ones, each of them was used as a validation, and the rest 4 splits was used as a training data set. So what validation strategy was used, that will be well documented in this. So if there was a test data set or a validation data set that was provided to driverless AI, so it will not do a 5-fold cross validation, but it would just use the validation data set for validation. So this strategy, or the one that you see here, would look different because it would be using the validation data set, not the cross validation technique. So this documents the model tuning. So the first tables shows the job order. So job order is something which is internal to driverless AI, but each row is a model which was tried during the tuning phase of driverless AI. So the job order 14, or basically the job 14, tried tuning a light GPM model, and the number of features was 63. And since this is an AUC which we were trying to optimize on, the scores will be all AUC. So the score of the model was 0.94, and the training time. So similarly, it will give you the details of all the models which are used during model tuning. And then it gives more details of each and every model, as in what was the tree method that was used. So it says like, okay, GPU histogram was used, and the grow policy was log loss, the max depth, the max number of leaves, and the other details which of the models that were used during the model tuning phase. And then comes the light GBM tuning. So for light GBM, we use the GPU hist tree method. The growth policy for the first one was depth-wise. The next two was log loss guide, and the last one again was depth-wise. And you get the other parameters as well that was tried to tune the model. So after tuning the model, you finalize which is the final model and what are the final hyperparameters which you want to use. So let's go there. So these are the few features and the feature engineering details that was done during the experiment. So this is not an exhaustive list. It just shows the details of a few features which were a part of the final pipeline. So if you look at the table on the left side, the first one says 6_text t, and it has a you cannot for instance, if you're looking at the feature name, you might not be able to figure out what exactly happened to create this feature. So we have a description here. So it says predicted probability of class 1 based on the linear model on TF-IDF feature from text column description. Internal parameters were 2, 0.01. So you get a better understanding of what the feature or the created feature means. And then it says, the next column says which transformer was used. So it used a bag of words regressor to create this feature. And then the final one is the relative importance of this particular feature for the final model which was built. And then the next feature is a cross-validated target encoding. So, and it will give you a description of it, and then the relative importance. So you get this this kind of a table for each and every feature. So this table would have the details of each and every feature that was a part of the final pipeline. And if you look at the right side, it says the dates transformer, which driverless AI uses. So retrieves any date or time values including year, quarter, etc. And then since date, it's showing you the date transformer because one of the features which would have been created for this particular experiment was transforming the date. And that's why it's there. So CV, and then the next one is cross-validated target encoding DT. So if you see the second feature on the left side, it has a CVTE description. So that's why there is some text around this particular transformer which was used to create a particular feature for this particular experiment. So basically what I'm trying to emphasize here is it will show you the details of only those features or the transformers which were used in this particular experiment, and not all the features which were there, or all the transformers which driverless AI has, and it can create features using them. Okay, I'll move on to the next slide. So this here we document the final model. So there were two light GBM models, and then it says like the final stacked ensemble pipeline with ensemble level 2, transforming 3 original features into 22 features in each of 6 models. Each fit in 3 internal holdout splits, then linearly blend them. So the final model is a linear blend of the two models which were built. So the model weightage is 0.66 for the model index 0 and 0.33 for the model index 1. And then it gives you the validation scheme for each of these models and the number of features that were used in each of these models. So the model index 0 model is using 22 features, but the other model is using 21 features on which the model was trained. And it has a few other details of the model index 0 and 1, like the tree method that was used, GPU hist, and then the maximum leaves that was there, maximum depth, subsampling rate, growth policy, and the column sample by tree. And similarly, it has details of the other model. And then you see the ROC curve for the model, and then the PR curve for the model. So this ROC and PR curve is for the final model, which is a blend of the model index 0 and model index 1, and not for the individual models. So this is another example wherein the idea is just to show that the AutoDoc will look different based on the experiment that you have ran. So I'll skip the slides which would look similar or are not different from the previous example, but I'll come to the ones which might be interesting. So here, if you look at the numerical columns, right? So it has ID, host ID, latitude, longitude, etc., which uh, for which you have the summary stats. So these are the input columns to this particular experiment. So as you can see, the data overview changes, and it has only the details of the data set that a particular experiment uses. And here, right, so the model tuning and features. So here here we are trying to optimize MAPE and not AUC. So it's showing those details. And then the final model here is a stack ensemble of one light GPM model and one XGBoost GPM model. So here in the feature evolution and the final model, we'll see the details of one light GPM model and one XGBoost GPM model. But in the previous example, there were just two light GPM models. So here it's again during the model tuning what all was tried, and so it documents it there. So this has the list of features here. So if you look on the right side, so there are no details of the date transformer here because the date transformer was not used for this particular experiment. So we have only details of like cluster distance transformer, cluster ID transformer, etc., etc. And then the final model here, the two models in the final pipeline is a light GPM model and an XGBoost GPM model. Uh, so uh, so yeah, so that's different for this particular experiment compared to the previous one. And then here for the validation, uh, so this is actually also predicted for the validation and the test data set, because for this particular experiment we had a validation as well as test data set apparently fed in. So this we come to last section, wherein the template which we went through for the AutoDoc of driverless AI, that's a standard template, but you can customize it. There are multiple different things which you can customize. For instance, in the model diagnostics, you can add in graphs which would, or the tables which would depict population stability index or the prediction statistics per quantile, actual versus predicted plot, Gini plot, etc. So that you can choose whether to show them in the document or not to show them. And in the in the diagnostics and new data set, you can configure whether you want to perform the model diagnostic on the list of new data sets and show them in the AutoDoc or not. And for the model interpretability, now you can now configure AutoDoc to whether to show the variable importance or not to show them. Similarly for the partial dependency plots and the ICE plot. So these are the standard techniques which we use in driverless AI for interpreting the model or understanding the model way better. So you can choose whether to show them or should those be a part of the AutoDoc or not. And how you do that? For instance, if you add in a config override which says AutoDoc underscore population underscore stability index equal to true, then the AutoDoc will have the population stability index table in there, which would look something as in the right side. And similarly for the prediction statistics per quantile, if you add in AutoDoc prediction stats equal to true in config overrides, it will give you this. And similarly for the variable importance. And same goes for partial dependency plots. So this is the partial dependency plot, and this is the partial dependency plot with ICE. So you can choose which one you want in the AutoDoc or which you don't want. So the AutoDoc is highly templated, and you can choose what subsections to show in there, and inside each subsection what all plots or what all tables should be there, or the ones that you don't want. So all of it is configurable using the config. So every time we are just overriding the config value. Like in this case, if you want the response rate plot, you just provide an AutoDoc response rate equal to true. If you provide it as false, this plot will not be a part of the final document or the final AutoDoc which gets generated. Similarly for the Gini plots. Yeah, so I think I missed the thank you slide, but yeah, that was more or less what I had to present. Now maybe we can take some questions, Saurabh.
Absolutely. Thank you so much, Nikhil.
Yeah. Okay, stop sharing my screen. Yeah, so can you repeat the question again, Saurabh? Yeah.
Yeah, how is AutoDoc different for the open source H2O3 and the enterprise platform that is driverless AI?
Yeah, so for driverless AI, we have a lot more details captured in the AutoDoc. As in for H2O3, you won't have the feature engineering details, like what all features were tried, or how many models were built to create those features, etc. And if you're just using plain vanilla H2O3 without the AutoML, you in the final model pipeline, you'll just have one final model. In case of driverless AI, you usually end up with a stacked ensemble uh, or a linear blend of multiple different models. So all those additional details are captured there in the AutoDoc for driverless AI, which won't be there for instance, an H2O3 model or a scikit-learn model. But when you build an H2O3 models, the model parameters, etc., will all be there. But subsections like feature, as I was saying, like the feature engineering, the model tuning, and uh, uh, and uh, and uh, and the MLI, the explainability part, like the partial dependency plot. So that might not, uh, all of them will not be there uh, for an AutoDoc which is generated for an open source H2O3 or for scikit-learn for that case. Does that answer the question? I hope so.
Yes, absolutely. Thank you. The next one asks, how does the auto-generated document fulfill compliance requirements for all countries?
Yeah, yeah.
Or do we have to do it ourselves?
Yeah, yeah. So the format which we ran through today, so that's something which the regulatory authorities in the US have proposed, and the AutoDoc is very templated. So now there are regulatory authorities in for instance, Southeast Asia, Singapore, that are coming up. So we have a slightly different template for those. And then the AutoDoc, instead of creating the template which we saw today, it would be populating the details in the template which is accepted by a regulatory authority in Singapore. So the conceptually AutoDoc is all template based, and you can choose and select what all details you want there in the AutoDoc and what all should not be there. So as we went through in the last section, or during the end of our presentation, that you can choose what should be a part of the AutoDoc or what should not be a part of it. So it's all very templated, and then you can configure the AutoDoc to be in a particular format which is accepted by a regulatory authority in a particular country. But the template which we went through is widely accepted in EMEA and US, and we have a slightly different template for Singapore. So yeah, I don't think India right now has a template as such, but we can use one of the templates which there. But if there is a new template in which you want to document it, that can also be plugged in very easily.
Thank you. The next question is, how much is the scope for document classification using AI as a research topic?
I don't know, no, but to answer to that, in the next version of driverless AI, which should be out in the first week of July, we have a lot of images and document classification which would come pre-built with driverless AI. So you just install driverless AI and you can do a lot of image related use cases, a lot of NLP document related use cases, etc. So so you can definitely have a look there. But we have seen a lot of customers solving a lot of problems using images of documents. For instance, say if you have your salary slip, for instance, right? So and there's a audit which you want to conduct, whether everything is in place, or a balance sheet of a company. So you can use different ML techniques, for instance, different variants of OCR to read in the images and then have your data stored in a particular format, and then you can do a lot of analysis on top of it. So there are a lot of use cases which people are trying to solve using an NLP on documents which are in form of images or maybe text, etc. So there's a lot of research that is going on, active research that's going on, and then NLP, like before COVID, I would say, like the NLP and the research in NLP was like at a high, at an all-time high. So 2019 beginning was, for instance, a lot of research papers and new techniques came out for images. But mid 2019 until before COVID, there was a lot of breakthroughs which were happening in the NLP domain. So that's what I would say.
Thank you, Nikhil. Next few questions are, on accessing driverless AI, pricing, free trials. So for that, please go to our website. There's a free trial available. You can take it for a spin, on-prem on our cloud environment. It's fairly straightforward, and if there's any hiccups, we're always available. There's another question
Just to add to that, Saurabh. So if there are any students here, so we have a university version of driverless AI, which you can download. If you have a university username or ID, you can download and install, use driverless AI for 6 months, and then you can keep renewing it till you are a student. So that's kind of free for students to play around, learn, and we also have university partnerships. So feel free to reach out to Saurabh for any of it. Thank you.
Awesome. Thank you, Nikhil. We are at the top of the hour. If you have any concluding comments, else we'll just wrap it up.
Now I would just like to say, like, thanks a lot, guys, for joining in. So this perhaps was the first webinar for AutoDoc, which we released like a couple of weeks back. So thanks a lot for joining in today. And
awesome.
Thanks, Saurabh,
thank
for
you,
hosting.
Nikhil. Thank you, Nikhil. Thank you to all the attendees for taking the time. Like we mentioned before, a copy of the presentation and the recording will be distributed in some time. Have a good day.
Thank you. Thanks a lot, guys. Bye-bye.